Alright everyone, how are we doing today? Alright, let's get back to work. Making a quick video for y'all. Welcome to 361, stochastic signals and probability. So the first thing I gotta mention is, well, what's a stochastic process? So, well, what does stochastic even means? Stochastic, well, means random. So what's an example of, well, random, or how do we explain what random is? So a good example is noise, but more specifically, white noise. And white noise is basically its spectrum in the Fourier domain as a function of f. F is just going to look like, well, this. It's just going to literally look like a flat line of white spectrum. You have, well, your base signals right here, and you have your really high frequency signals, and it just is an addition of all these signals to create, well, in the time domain, f of t, just a bunch of random noise. So it's just going to be like, or whatever you want it to be. It's just noise. And then you're probably saying, oh, well, noise, what does it do? Well, if you think about it, well, noise is just noise. It's really, we really shouldn't be worried about it. However, actually, let's start with our problem. Our problem is, well, suppose we had a resistor, right? And suppose I throw in a signal that's periodic, right? Like a sine wave. What's the average value at the output of this resistor? And well, that's 0. And does that mean, like, oh, if you have a light bulb, does that mean we are energy efficient and have no power? No, not exactly. So what you have to do is you have to square the value so that all the negative peaks turn to positive, and now you get your average power. The same thing with noise. If you square this noise, square it, you're going to get, well, something f squared of t. You're going to get something like this, and now you have something you can measure in an oscilloscope, you know, OSC. You can measure that if you wanted to. And that means we get power from this noise. So if I wanted to make a brief introduction, actually, let me click on this. Oh, there we go. SNR is basically the signal, signal to noise ratio. So the ratio between the signal and the noise. So you're probably saying to myself or telling me, hey David, if we have some system h of n, x of n, and y of n, wouldn't it be better to look at, oh, the output in terms of the input? Like, well, yeah, but that's literally our actual system itself. In reality, engineers like to send signals from one point A to another point B, and all we worry about is, we're not worried about if our signal does anything. We're worried about if our signal gets to our place. It's going to go on a crazy transmission line very far, and all we care about here is our input x, x of that's going to trigger me right there. Yeah, because you got to put a square on it to make it look like power. You'll notice that you'll get some noise that just pops in here. Let's just call it a noise. And all we worry about is, well, what does our input signal look like divided by noise? Like, how much of it do we get? Ideally, if noise is 0, SNR is going to be infinite, which is great. But this is the real world, so this is going to be a real number. But if you wanted me to show you something, you see this floor. Okay, let me show you one more big example. So it's a spectrum f. If I had a noise, like, or a desired signal, you know, a signal you're putting into a system, right? That's our x. And then you have this noise floor that's just naturally humming down somewhere pretty low. If you, depending on your wires, your components, or whatever you got white noise, you got red noise. Red noise looks like like this. You have bassy signals, and then pink noises. Oh, okay, you guys want me to get there? I'll talk about that. This is not pink, whatever. Pink noises like that too. But point is, you got lots of types of noise. But what I'm trying to say is, if you have bad noise, as this noise floor goes up, you're going to see that the ratio between this and this, it gets smaller. That means you get poorer SNR. So what I'm trying to say is, yes, noise is something to worry about. It has power in it, and it does sad things to our systems. So what I'm going to get to is, well, what is power? What is variance? Variance is, well, grab another piece of paper. I want to make this video quick. So variance, I like to write it like that, is basically the average of the input squared minus the average of the input squared. So the mean squared minus the mean squared. So very weird way to think about it, but point is, this is how we do the calculation. So you're probably saying, okay, what do we do? How do we calculate variance? So let's suppose we pick a signal which is going to be minus 2 rand n1 minus 1. So that means you're going to get a signal which is going to, in the time domain x of n, it's going to bounce around, just whatever, from 1 to minus 1, right? So this is what your signal is going to look like. And the change between 1 and minus 1 is 2. So this is your random noise function generator. So if you ever needed noise, use this. So now you're trying to say, well, how do we calculate this? So e to the, do I want to get to that point? Actually, let me get to this one. Let's talk about PDFs. So probability density functions. So it's basically, well, something where we can see what the probability of a signal, or what's the probability of a value at a certain, well, what's the probability of any value. So what I'm going to try and explain it to myself as practically as I can. You see our input signal, what's the probability of it being at 1? And then what's the probability of it being at minus 1? And then everything in between. We're going to assume it's constant. And let's call this constant C. And now we're trying to look for the probability, I'm going to write it like this, of X. And there's a holy rule I want you all to memorize. If you don't memorize this, you'll be sad. PDFs. Okay, if you don't memorize this, go home. If we go from minus infinity, so to infinity of the actual function itself, px, dx, which is equal to 1. So what I'm trying to say is, if you take a huge integral, just all of it, you'll always get an average of 1. You gotta memorize this, okay? Memorize this. There you go. So how do we use this to like solve for this problem? So, okay, we don't know what C is, so let's just do our happy integral itself. Px, which we call, C, this is a function of x, I think. Whatever. Point is, let's just remove that. C dx is equal to 1. Now let's do our handy dandy formula, which is C, then x from minus 1 to 1, which is equal to C of 1 minus minus 1, which is equal to 2C, which is equal to 1. C is equal to 1/2. There you go. So what I'm trying to say, and you got to memorize this for the rest of your life. If you don't, you'll see it eventually at work, is all noise or white noise with this type of 1-to-1 will always have this kind of factor. And if these spread apart, then this C goes down. So remember that. So if you're going from 1/2 to 1/2, it's not 1/2, or you know what I'm trying to say, right? Okay, if this was 2, minus 2. This was 2, just in case he changes it on you. Then this height would probably be 1/4. Okay, remember that. Hint, hint. So now the next thing I gotta get to you is, well, let's calculate this one, the average. E of x, which is equal to -1 to 1. Did I actually write this equation down? And that's okay. You guys will figure that out. Which is going to be 1/2 x dx, which is going to equal 1/2 x squared divided by 2 minus 1 to 1, which is equal to 1/2 or 1/4. Actually, yeah, 1/4 1 minus 1 squared minus 1 squared, which is equal to, this is a plus, but that means 1 minus 1. 1 minus, yeah, 1 minus 1. Whatever, you know what I'm trying to say. Zin equals 0. So we have the average of noise is going to be 0. So now our next thing we gotta do is we gotta calculate this puppy. All right, you guys learning? You guys getting your money's worth? No. Oh man. Yep. Wonder how everyone's doing in this class. You guys even watching the videos? Only yours, David. Oh man, I feel flattered. It's okay, don't worry. So now let's calculate e to the x squared, inside squared, which is basically equal to that same thing. What's the probability of x being at -1 or 1? 1/2. Or anything between that. -1 to 1 of x squared dx, which is equal to 1/2 x3 divided by 3 from -1 to 1 is equal to, let's do this, and then let's do -3 minus 1 3 cubed. But because it's cubed, I mean this cancels out with this. Adios this term. Do we need to? Oh, hold up. That one comes out. Wait. Let's do this. 6. There we go. 6. This is equal to 2/6, which is equal to 1/3. Okay. I was just panicking for one thing. So that means what I'm trying to say is the variances of x is going to equal 1/3 minus 0, which is equal to 1/3. Boom, you're done. Hooray, you can punch this into MATLAB, and actually you can verify this with MATLAB, and I will show you your assignment right now. Oh yeah, looking at probability. So let's look at a specific problem. Let's look at this. We're gonna look at this, and well, Dr. You can watch a video from Dr. Stewart about this. Oh, there's his name, by the way. Oh, look, if you go to your assignment, you'll see this word all the time in all his bottom texts. So he shows you how to do this, and I will show you, well, what I have. Let me show you example 4. Run. Aha, there we go. So if you calculated it right, you're gonna get this graph. So we took 10,000 samples, 10,000 samples, and we just threw them into bins, right? What's the probability here? And like, oh, you can see it's kind of uniform, and that kind of looks like, oh, and I created this probability density function. So divide all these values, or the amplitudes, by I think n, and then try to shift it, because, well, actually, yeah, it is shifted here too. And then you see, look at that, you get that half. You guys learning anything? There you go. Sweet. Half minus 1 to 1. And that looks exactly like, I can actually double screen this. That looks like this. Hey, you see? See, they kind of match. There you go. And then this summation right here is called a cumulative distribution, a CDF, I think. CDF, yeah. Cumulative distribution function, where we just add all these points. I think that's what we do. Yeah, we add all the averages or the probabilities, I think. And well, every time we add, the probability should add to 1. So if you take the integral of this, you get 1, I think. No. As you sweep here, if you add this plus this, you get that. Down. So you guys can look into that some more. So that's number 4. So if you know how to do that one, then I think you can do everything else. I think everything should be pretty cool. And what's this? Zero mean ergodic random process. A variance of 1. Yeah, I'll let you guys figure that out. I think he does it in the thing too, unless I have something different. Let me see. Wonder how he does it. You guys will figure that out, but okay. Let me get back to the other thing what I was trying to show you. Let me show you this set of code. Just gonna have to pull it out right here. There we go. So if I grab this, okay, let's not make this video too long, David. There we go. Boom. So there we go. To prove your hand calculations, the mean of x as a function of n, and then variance of x. There we go. And then you can run this puppy and array must have why is it barking at me? Mean. Okay, if I calculate this, I think it doesn't like me for some reason. Did I make a function? Oh, this should run. X. There we go. And that should run. Oh! Mean. I think I overwrote it. Clear vars. And let's do this. There we go. So what happened was I stored something into mean and then I just completely destroyed the function. Don't do what I just did. Make sure you make unique names that are not variables of things that have already been created in MATLAB. This is a function, this is a function, and boom. And what I'm trying to get to you right here is, look at that. Oh, what's that? That is 1 divided by 3. See that? Well, this is not an engineering format though. Unless I will show you engineers. 2.3f. Yep, I know a lot of tricks in this game, man. There you go. You see that? Engineering format. That's not engineering format. That's the floating integer. 2 decimals to the front, 3 decimals in the back. Okay, you don't believe me? 5. There you go. And that proves our hand calculations. So everything we just did, is it making sense? Are you understanding this? Are you getting your money's worth? Are you? No. Oh man, don't blame you. Okay, so the next thing I gotta show you, and I actually might jump right into the actual assignment itself. I'm just gonna go real hard on you guys. Alright, so let's go to the actual assignment. So this is the hard part that I didn't figure out back when I was an undergrad, but now that I've taken a bunch of grad classes, I kind of feel like, oh wow, I could have gotten this, but I made a mistake. Consider a discrete linear shift invariant system. So I will write that right here. Actually, let me see if I can do this. Oh yeah, we can dual screen this. You guys are getting a lot for education. There you go. So, actually, let me just figure out what it wants. So, determine the mean and variance of the input. Okay. Determine the mean and variance of y when x is a uniformly distributed ergodic process. I think that's another fancy way of saying random. So I will get to the point of this. If you want to know the average of the output, or not the average, the power of the output, the variance, which is basically x powered, and then you got this function right here from minus infinity to infinity of h of n. There you go. So this is your formula, and you're probably saying, oh David, I don't know how to use this function, like do I have, and you notice that this is an IIR, it's infinite. You put in something and it just cycles back on itself. It's do I know how to draw this one? Okay, I'll try to draw it direct form 1. If it's direct form 1, that means it goes into the gains. Yes, the gains. No, it goes into its delays. There we go. Alpha, I think. There we go. And let's put a minus there. Sweet. Actually, I think it's plus. Yeah, it's plus. So if you punch in a 1 here, what's the probability that the 1's gonna roll in circles? Infinity. Or it's always gonna roll back into itself. So there's a neat trick that you guys should really consider. So actually, okay, knowing that this x variance of x is literally let's see. Okay, actually it shows right here, using the rand function, generate x, and it gives you x, and hint, we just did it right here. So you already have the answer. You already know it's going to be 1/3. So that means this right here is going to be 1/3. Okay? You know what's going on, right? How do you calculate h? Don't think deep. H of z is equal to 1 divided by 1 minus 1/2 to the z to the minus 1. Remember the Laplace transform, the Fourier transform, the z transform, the other transforms, yada yada yada. What's the inverse z transform of this function? Oh, if this doesn't ring any bells for you, well, let's look at h of n is equal to alpha of n u of n. And if we do the h of z, let's call this one a prime to differentiate the two. If you take this to infinity, 1 minus alpha z to the minus 1. See that? Oh, they look similar. Therefore, your h of n is going to equal 1, or no, there we go. Transforming this from here is going to equal 1/2 n u of n. Okay? Not so scary, right? Now, punch this right here. Oh, I forgot a special term. If you forget this, you will cry. I will promise you. I will guarantee you that. Because if you try to multiply this by this, you're not going to get the power. You're actually going to get the cross correlation between these two. And that's not the right answer. To get the right answer, you have to square this h term. So now that you know that, let's finish this up. What page am I? Don't remember. 3, yes. Let's punch this right here. Let's finish this puppy. Y squared is equal to x squared. This is power, by the way. Of, well, let's just do this. Do you mind if I skip steps? Of 1/2 n u of n. Actually, we have already used the u of n function. The u of n destroyed this guy, so it forces it to 0. Squared, which means of 1/4. You can put the 2 in there, but we like it like this. And remember that one crazy rule where the series, I think I forgot how to explain it to you, where if you do, let me see. Oh, yep, I'm firing all brain cells right now. Of n, let's assume this is n minus 1. This is 1 minus alpha of n. See this one right here? For if alpha is less than or equal to 1. There you go. Remember this one right here? So we have this equation right here. So as n goes to infinity, this term goes to 0 if a is a small number, which means x squared, don't forget that one, this is going to equal 1 minus 1/4. Remember this, okay? Remember how we're doing this. Remember, we're going from this happy transfer function, this h to z, to our time domain. You know how to do that. Trust you do. And boom, we can get to here. But we know that this is equal to, see this term right here becomes 4 divided by 3, which is equal to 1/3 times 3 divided, nope, 4 divided by 3, no, sorry, getting ahead of myself, 3 divided by 4, which becomes 4 divided by 3, 4/9. You see where we're going? And you're like, wow, David, what's going on? I will show you. I will save you, undergrads. Don't worry. Aha. Suppose I just copy pasted. Suppose I give you the answers. Well, this is not the answer. Well, yeah, this is how you verify your answer. Here's the, oh, let's do mean E, mean E, mean Y. There we go. Oh, let's put a 0 right there. I forgot. -1. Okay. It didn't bark at me like this. Why now? Why here? Why now? Let's get it from the source itself. Clear variables. There we go. Boom. I don't know why it didn't work. I probably has some function there. But let's look at the variance of y. This is the whole meat and cheese of this class. You guys are gonna love this one. 3. Oh, what's this? Let's do 4 divided by 9. And look at that. Our 4 divided by 9 that we hand calculated is close to our variance. Let's actually pump up some numbers there. Look at that. You guys learning a lot? I know you guys are. Don't worry. You guys are gonna do great on this exam. So now you know how to do that. This problem's not scary. Actually, okay. Let's just finish this puppy up. Minimize this one. Let's get right down into this. Generate. I'll let you do this one. Generate. Actually, no, because I actually haven't done it too. However, I'll probably show you how to do it. Okay, let's just go right into this puppy. So what I'm gonna go for you guys. Let me show you this. I have a presentation for you guys. the Fourier transform, FFTs, and frequency responses. So remember that happy old computer assignment 3? You were like, oh, and I assume you guys watched the computer assignment 4. I went through the derivate, like how to derive this function. We made this a function in the last video, the discrete Fourier transform. But if you want to copy that, go ahead. But if you don't know what's going on, I don't recommend it. But this basically translates these alphas into something more human readable, a single-sided spectrum, a Fourier transform to be exact, which looks like where's my Fourier transform? There we go. Fourier transform, something you can easily human read. Okay, back to the thingy. So here's our input x divided by the number of samples. That's what MATLAB does. This doesn't actually do what you want it to do. You have to divide it by n to get the actual average alphas. We're doing the same thing with the output spectrum, the FFT. And then I use this handy dandy formula. You should all look into the last video to understand why I did this. I actually went bit by bit on how to actually build this. And here's our frequency domain. And now let's do this. F9. Boom. And you're probably saying, what's this, David? It's noise. It's literally noise. This is their input spectrum. And it looks pretty good. If you add all this up, it should equal to 1, I think. But it's okay. Now let's go to this. F9. Oh, what's going on? Do you understand what's going on? You see this noise right here? Then you see this noise right here? That's really interesting, okay? And this is the whole point of this assignment. You gotta think. You gotta fire up those brain cells. And look what I'm about to do. You can do this if you want to. Oh, what's that? Comparing our input noise to our output noise. And it looks pretty cool. So, what this is supposed to look like, and I thought I had a much prettier graph. I thought I did. It's whatever. Wait. Darn. Oh wait, that's as beautiful as it gets. Okay, never mind, screw it. What's going on here is, and this is an advanced topic if you take ECG722, which is mixed signal design. This is noise shaping. So what we're doing is we're shaping the noise. We're actually not getting rid of the noise. We're just pushing it somewhere else. So this is a very practical thing. They do this all the time in industry. They do this a lot in mixed signal design when they're making delta sigma modulators. So they're making like crazy DACs that push this noise. Actually, a delta sigma modulator DAC, or ADC, ADC, it pushes the noise, well, this white noise, let me get that white noise. It pushes this white noise up to the spectrum. If you don't understand what I'm trying to do, let's grab this puppy right here. What we're trying to do is we're taking this noise and we're just shaping it using some noise shaper. If we had our filter function, then our resulting noise should be, oh, we have less noise here, but we have more noise right here. So that's what I'm trying to get to you, is we're using a filter to not just modulate noise. Noise modulation is the proper term of saying that. So now you're saying, what's going on here? All right, let's go over it. And that's what I have right here. Let me just copy paste this for y'all. Yes, to do an FFT. Here we go. This B is our, this is the numerator term. Now we're looking at the denominator term, which is 1 minus 1/2. 1 minus 1/2. And the frequency response. And then, because we're engineers, we like power. And let's semicolon that. And because I gotta rush this out because I can't waste so much time. We are at 34 minutes, perfect. And let's run that puppy. And here you go. Do you understand what's going on? The whole point of me trying to carry 361 as much as I can is to make sure you guys know what's going on. You guys are getting your money's worth. And here you go. So you see that this is the filter. We're multiplying noise, white noise spectrum, to this filter, and it's giving this modulated noise. We're getting higher power here. However, we're getting little power here. But if you do the average RMS of this, well, you get the average power. You actually get, well, it should ideally be the same, but the point is, if we're looking at just a couple of points or things, we're going to get more power here, less power here. For an ideal delta sigma modulator, it should be the other way around. This filter should be flipped. Could I make a filter? Let's build a filter. Let's make this one. Let's show you what a delta modulator does. 0.9. This should be a low pass filter. It's not doing what I want it to do. Oh, because I lost it. Minus. There we go. Oh, but that's because I gotta change the actual. Watch this. Watch this. Watch this. You guys will be proud of your TA. Kind of. Ooh, that's gonna change the problem a lot. It's okay. We're learning. You guys like getting your money's worth? N-1. Oh, common mistake. Oh, 0.9 times. Oh, there we go. Run. And let me show you what a delta sigma modulator. There we go. That's what a delta sigma modulator kind of is. We try to cut the noise off, and then we push all this noise to the high end, because what we want to do is, suppose we were using like oversampling. If we push this to like 1 billion gigahertz, yes, 1 billion gigahertz, very fast, that means our operating frequency can be like in the megahertz range, which is a usable frequency. And all we get is this pure, beautiful noise, or input signal. So if you put a sinusoid, you get no noise. Look at this noise, red. It's gone. So that's the whole beauty of this. This is the whole reason why I'm helping you guys out with this. I hope you guys learn a lot with what I'm trying to show you. And let me just go over. Oh yeah, so the filter function to generate this. Well, all you got to do is, you know your B. Here's your B. I changed it. You know your A. All you got to do, I don't know, help filter. Let's do this equation and you're done. BAX, which is noise. All right, everyone. Hope you guys enjoyed this. It was a pleasure doing more videos. I think I might have one more to do. That's if I have more time. I have to get going on this one. So with that, take care, y'all. Have fun.